So, welcome back to another video of computational methods, where today we're going to be discussing the idea of root solving. Okay, and we'll start off with the most simple algorithm, that being the secant method, because it relies on not very much or any calculus entirely in algebra. And the easiest way to describe the secant method is with this diagram. It entirely relies on picking two initial guesses, x0 and x1. Okay, we're finding the root of this f of x function here, this red line, and you see, hey, there's a root right there. I found it. Okay, and the algorithm goes as such. You pick two values, x0 and x1, and you draw a secant line between the two. Wherever that line crosses the x-axis will be your new x value. This will become x2. You throw away the lowest x value, you throw away x0, and you designate these two as your new values to draw a secant line. And you continue as such. You draw a new secant line, this will be your new point, and you throw away x1, so on and so forth until it eventually converges on a root. Okay? And the Wikipedia page provides the formula for it, and you're able to go off and do some algebra to go off and find an expression for, hey, what is the expression for my next x value where it crosses the x-axis? Okay, that being the secant line. So let's try this out. So I've gone ahead and defined a function here, and you notice mathematically I have a root at 8, a root 0.8, root at 0.3, and a root at negative 0.5. Okay, and you see it as such here. So let's go off and define a secant method. So define secant. What does secant want? Well, it wants a function to root solve and two initial guesses, right? And with these algorithms, we're introducing the idea of we want to designate a maximum number of iterations. Otherwise, the algorithm might run forever, right? So let's do 50 for this one. We'd also like to define an idea of tolerance. Again, otherwise the algorithm will run for a long time. We want to try to be as perfect as possible, but I think 1e to the negative 12 is perfect enough in my eyes. Okay, so first order of business, let's define our f0 and f1. f0 being f evaluated at x0, right? And f1 being f evaluated at x1. So we can start our algorithm now. So for I in range max iterations, and I'd like to find my new x value. So x2, okay? x2 is equal to f1 times x1 minus x0 divided by f0 minus f1 plus x1, okay? And with my new x value, I can find my new f value, and f evaluated at x2. So at this point in time, I'd like to check, hey, am I close enough to 0 yet? So if, remember, absolute value, so np dot absolute value, if f2 is less than or equal to the tolerance, what should I do? I should break from the loop. If not, I should go ahead and update my values and throw away the oldest value. Okay, so f0 is equal to x1 f1, right? And my new x1 f1 should equal x2 f2. Right? Notice here that I'm essentially throwing away my old x0 and f0 values. All is said and done, I should return my solution wherever my root is, and let's throw in f2 as well to see how close we are. Okay, so with that we can go secant f. Let's try and find this root right here. Let's try and find the 0.3 root. So let's guess. I think it's somewhere between 0 and 0.6. Yeah. And would you look at that? It found it to a pretty large degree of accuracy, and it says, hey, I'm at e to the negative 16. I think that's close enough to 0. So you see that this is a pretty effective method for finding a root. If you are, I don't know, took pre-calculus within the early 2000s, I bet you used ATI 84, and there was a root solving function that asks you to find have two initial guesses of where you think your root is going to be. So that is the secant method. This is the algorithm by which that TI-84 finds that root. Okay, so next video we're going to go to a bit more advanced method called Newton's method. So we'll see you in the next part. Okay, so let's go off and derive Newton's method. Okay, so it's a step further from secant method, whereas previously we had two two initial guesses. Newton's method only relies on one. The way it does this is, from that one guess, it computes the derivative to find the tangent line and finds the new place where it crosses the x-axis and treats that as the new iterative guess. It'll iteratively solve for the root that way. Okay, so that's the basis of Newton's method. Rather simple. Okay, the nice thing about Newton's method is that we can go off and expand it to a complex functions. Okay. Where we have k variables and k functions, okay? And from Wikipedia, you find this expression here, okay? And from here, we'll be working in the realm of jacks. So let's check out, well, I've imported an example function, and let's evaluate it at 0, 0. Well, you know, it's not quite a 0, okay? So, but it seems like a good guess to start off with. So let's define a Newton, let's call this Newton k. Okay, so for k values, k variables, k functions. And what does it need? It needs a function to solve the root of an initial guess, and the same arguments above, this maxiter and tolerance. Okay, maxiter and tolerance. We go off and, well, first thing we should do is let's find the Jacobian, because we're eventually using the Jacobian, right? So let's go do f underscore Jacobian equals jax.Jacobian of our function f. Okay. Well, let's keep going. With f, let's call this f naught, and it's going to be f evaluated to x naught. Okay. So we can go off and start iteratively solving our function now for the root. So for I in range max iterations, so that's going to be our for loop. Okay. And what first thing we want to do is to, well, calculate the new x value where it crosses the x-axis, and it's based upon this formula here. Okay, so what it's saying is the new x value is going to be equal to previous x value minus the now be careful here, the Jacobian. So remember, Jacobian is a matrix of partial derivatives evaluated at the previous x value and taking the inverse of. So it's a inverse matrix operation. So we'll do jnp dot lin alg dot inverse. Okay, inverse evaluated at the previous x value. Oh, actually, f underscore Jacobian evaluated at the previous x value. That's what I was looking for. Okay, and multiplied, not just any multiplication, matrix multiplication by the function evaluated at the previous x value. Okay, that's our new x value. We can go off and calculate our new f value, that being the function evaluated at the new x value. Okay, at this point in time, we'd like to check, are we close enough to 0? So if f, you'd be tempted to go off and if f1 is less than or equal to the tolerance, then we would break. Okay, note that it's a vector. It could be a vector function. It could be a vector function, meaning that, well, there's more than one f value. So what we want to do is to find the norm. In other words, the magnitude of this function. Okay, jnp.lin alg.norm of this matrix. Okay, so if it's not, we go off and update. We should say that our new previous x value is equal to the new x value, and our new previous f value is equal to f evaluated at x naught. Okay, and this will end if the for loop reaches our maximum number of iterations, and we would like to return our x1 and x2, x1 and f1. Okay, so let's go off and try it. Newton k for a function f evaluated at let's do jnp dot array. Let's do our initial guess at 0, 0 again. Try it out. And would you look? Oh, not f. We don't want f. We want fun. That's our new function. And would you look at that? it converges on a solution, that's our solution, and it shows us that, hey, I've got 0 and something pretty darn close to 0, 10 to the negative 17th. Okay, so I'd like to leave you some closing thoughts about Newton's method. You notice that it's really simple. It's a pretty quick video today, and well, it is such that it's possible to use it for multiple equations. And remember, where is it? You know, and k variables, k functions, but it relies on this inverse function here. Within the world of computing, the inverse function is a very expensive operation. So for any real amount of numerical analysis, almost nobody uses Newton's method. Even though it's rather simple, it's extremely expensive and slow. So imagine you have 100 functions and 100 or more independent variables. That will be an extremely slow algorithm to complete. Another thing is that you'll also be noticing that root solving seems the natural progression of root solving may be minimization and maximization, right? Because if you recall from calculus 1, basic calculus, the first derivative, the roots of the first derivative of any function will provide the critical values of that function, that being the maximum and minimum. So I think you can see where this will progress next, okay? So with those closing thoughts, we'll see you in the next video where we'll be deriving Broyden's method, okay?